Hi class, in this video we are going to talk about chapter 7.3 Solubility Equilibria. So the learning outcome will be to be able to define solubility, molar solubility, and solubility product KSP. To calculate KSP from the concentrations of ions and vice versa, predict the possibility of precipitations of slightly soluble ionic compound by comparing the values of ion product Q to K. Define and explain the common ion effect. And lastly, to perform calculations that relate to common ion effect. First of all, the first term that you need to understand is the term's solubility. So solubility is defined as the number of grams of solute dissolved in 1 liter of a saturated solutions. Given the units here is gram per liter. So we have the mass of solute over 1 liter. So which give you a unit gram per liter. And there is another term which relates to solubility is what we call as the molar solubility. The molar solubility has a symbol S. So every time when you look at the symbol S, it is referred to molar solubility with the units mole per liter. So this molar solubility is defined as the number of mole of solute dissolved in 1 liter of a saturated solution. So we can also write it this way. So number of mole of solute over the volume in 1 liter, which give you the unit mole per liter. So you need to understand the conversions between solubility, gram per liter, into molar solubility, mole per liter, and vice versa. So from solubility into molar solubility, we need to divide the molar mass. And from molar solubility into solubility, we need to multiply the molar mass. So let's try a simple examples below. Alright, so recall that the gram per liter refer to solubility, the mole per liter refer to the molar solubility. So if we want to convert from gram per liter into mole per liter, you need to divide by the molar mass. And at the other side, if you want to convert from mole per liter into gram per liter, you need to multiply the molar mass. So the first question is over here. Convert 5.80 gram per liter silver chloride into mole per liter. So in this case, the molar mass of silver chloride, I given you over here is 143.4 gram per mole. So using 5.80 gram per liter, if you want to convert into mole per liter, you need to divide by the molar mass, 143.4 gram per mole. So in this case, gram and gram cancel, and it will give you the unit mole per liter. Okay, so the value you just do simple calculations, which give you 0.04 mole per liter. Bear in mind that mole per liter can use the capital letter M, the unit same as the concentration. Secondly, convert 2.4 mole per liter. In this case, we're still using silver chloride, okay, into gram per liter. So 2.4 mole per liter. If we want to convert into gram per liter, we need to multiply the molar mass. So 143.4 gram per mole. So in this case, mole and mole we can cancel, which give you the unit gram per liter, which is what we want. And the values over here give you 344.16, the values in gram per liter. So the next term we have here is solubility product constant KSP. So solubility product constant is defined as the product of the molar concentrations of ions involved in equilibrium, each raised to the power of its stoichiometric coefficient in an equilibrium equation. So this K is similar like when we are in chapter 6, we're doing the Kc, Kp, and so on. But the Sp stands for solubility product. So whenever you see the capital letter K, it refers to a system in equilibrium. So given examples over here, we have a saturated solutions of silver chloride in water. So the silver chloride is what we identify as a very slightly soluble ionic salt. So the silver chloride over here, we will write as the solid phase. Okay, because sometimes it will dissociate and dissolve in water, and sometimes it will remain as the solid, which is your precipitate. So we will look further into this one in a later page. But first of all, you need to understand about the solubility product constant KSP expression. So silver chloride solid, when it dissociates and dissolves in water, you will dissociate into silver ion Ag plus and chloride ion Cl minus, and both exist as aqueous phase. So when you want to write the KSP expressions, again, concentrations, we only take into account the species at aqueous phase and gaseous phase. So solid, we just excluded. So the KSP expression, we have the concentrations of silver raised to power 1 because coefficient is 1. Cl minus also raised to power 1, coefficient is 1. So the terms explanation is in the green box here. The solubility equilibrium equation shows the silver chloride, which is the solid solute, dissolve in water to form silver aqueous ion and chloride aqueous ion. So in the saturated solutions, the amount of dissolved and undissolved solute are in equilibrium with one another. So the terms saturated says that you have a balanced amount between your solid silver chloride and also the ion, the aqueous ion Ag plus and Cl minus. So dissolved and undissolved silver chlorides are in equilibrium. Again, when we say K, we refer to equilibrium. So the rate of forward reaction is equals to the rate of reverse reaction. So value of KSP indicate that the solubility of a saturated solutions of ionic compound. In another simple words, we want to see how far a solid salt can dissolve. Does it has a higher solubility or lower solubility? It all depends on the value of KSP. So if we have a higher value of KSP, it indicates that the solubility is higher. So at the same time, if you have a lower value of KSP, that means this ionic salt has a lower solubility, or it is less soluble. So the example given over here, we have lead chloride, okay, PbCl2 with a KSP value 1.7 times 10 to the power of -5. And we have PbI2, lead iodide, with a KSP value 9.8 times 10 to the power of -9. In this case, lead iodide, the value 9.8 10 to the power of -5 here is smaller KSP, which indicate that the solubility is lower. Or we can also say PbI2 is less soluble, okay, compared to PbCl3, which the value is higher, okay, and higher KSP value indicate that it has a higher solubility. Alright, so PbCl2, which has a higher value of KSP, has higher solubility, or it is more soluble compared to PbI2, which have a smaller KSP value. So from here, you can identify how much or how far a salt can dissolve. And the last point over here is similar like the KCKP. So KSP, the equilibrium constant, will only affected by the temperature. So as the temperature increases, solubility increases. Therefore, your KSP increases. So now we have already learned the term solubility, molar solubility, and solubility product constant. You need to identify and distinguish between these terms. So solubility, or if you have the symbol S, which refer to molar solubility, it refers to the quantity of the solute that dissolve to form a saturated solutions. So it has a unit gram per liter or mole per liter. Whereas for our solubility product constant, symbol is Ksp. So this is an equilibrium constant for the equilibrium between an ionic solid salt and its saturated solution. And there is no unit for Ksp. Bear in mind that Ksp is to measure how much a solid salt can be dissolved to form a saturated solution. So let us try our example questions 1. Write the solubility product Ksp expressions for the following ionic compounds. So first of all, we have our lead fluoride, okay, PbF2. So PbF2, all the examples given over here is the very slightly soluble ionic salt. So the phase will be in solid. So we begin with PbF2, which is a solid, and it is in equilibrium to dissociate into its respective ions. So in this case, we have Pb2 plus aqueous and F minus aqueous. And to balance up your equation, 2 fluorine on the left, and then we have 2 fluoride on the right hand side. So this is your balance equation. So to write the Ksp expressions, remember K expressions, we are taking the concentrations of the ion, the aqueous ion, and then exclude the solid phase salt. So in this case, Ksp equals to Pb2 plus raised to power 1, and for fluoride ion F minus raised to power 2, since you have a 2 for the stoichiometric coefficient. So this is your Ksp expression. And then for questions 1b, we have calcium phosphate. So we have a solid ionic salt over here, and then in equilibrium to produce its respective ion. So in this case, we have the calcium 2 plus aqueous, and we have the phosphate ion 3 minus aqueous. To balance up the equation, 3 calcium on the left give you 3 calcium ion on the right. And then phosphates, you have 2 molecules of phosphate. Then we write out the Ksp expressions. Just take the aqueous ion only. So we have our calcium ion Ca2 plus raised to the power of 3 because stoichiometry is 3. And then we have the phosphate ion PO4 3 minus raised to power of 2 since coefficient is 2. So remember, coefficients will become the power in your Ksp expression. And then for your C, we have our silver carbonate. Please also practice, if the questions give you a name of a compound, you need to come up with the correct formula. So silver carbonate, it has the formula of Ag2CO3. Since the ion for Ag is Ag plus, and then ion for CO3 is 2 minus, so it gives you 2 molecules of silver. So solid dissociate into Ag plus, the aqueous ion, and CO3 2 minus, the aqueous. And then balance up your equations to give 2 silver ion on the right hand side. So once you balance the equation, then only proceed to your Ksp expression. So Ksp equals to silver ion raised to power 2. And then the concentrations of carbonate ion. So here is your Ksp expression. Next we have our barium chloride. Barium is from group 2 and then chloride is from group 17. So which give you a barium to a Cl2, BaCl2. So please practice the formula. Barium 2 plus Cl is -1. So cross multiply over here give you BaCl2. Make sure that you have the correct formula for this ionic compound. Okay, so this solid barium chloride dissociate in equilibrium to produce Ba2 plus aqueous ion. and 2 ion of Cl minus aqueous. So this balance equation will give you the Ksp expressions equals to Ba2 plus raised to power 1 and then Cl minus raised to power 2. Next questions, we have copper sulfate. Again, Cu, we have a positive 2, sulfate, we have negative 2. So the balance charge gives you a formula of CuS. So copper sulfide, solid, dissociate in equilibrium to give you Cu2 plus aqueous ion, and then sulfide ion aqueous. So the Ksp expressions equals to concentration of Cu2 plus concentration of sulfate ion 2 minus S2 minus. Last one for F is ion hydroxide. So in this case, the ion gives you a positive 3. If you see over here, it means that this ion has a positive 3 charge. And then OH, we have a negative 1 charge overall. So FeOH3. So Fe in bracket, we have 3 molecules of OH minus. So the formulas over here, FeOH3, a solid ionic compound, dissociate in equilibrium to give you Fe3 plus aqueous ion and 3 molecules of OH minus. So the Ksp expressions, Fe3 positive, and then the OH minus concentrations raised to power 3. So here's the answer for D, E, and F. For example question number 2, write the solubility equilibrium equations based on the following solubility product expression. So in the questions over here, it gives you the Ksp expressions and you need to write out a balance equation. So for A, the Ksp value equals to the concentrations of silver ion raised to power 2, which indicate that there's 2 Ag plus ion. And you have a power 1 for the sulfate ion, which means you only have 1 molecule of SO4, 2 minus aqueous ion. So in this equation, it will be in equilibrium with the ionic compound Ag2SO4 solid. So how are you going to figure out this formula of salt? So similarly like before this, so silver you have a positive 1 charge, and then for the sulfate ion you have a negative 2 charge. So figure out the formula for the salt, so Ag2SO4. So this will be the formula for your ionic salt. For B, the Ksp expressions give you 3 molecules of, or 3 ions of Na2 plus. As the power is 3, therefore the coefficients will be 3. And then there's 2 molecules of the phosphate ion, which means there's 2 molecules in your equation. So 2 PO4, 3 minus aqueous. Alright, and then predicting your formula, and A have a positive 2 charge, and then for the phosphate, you have a negative 3 charge. So cross multiply over here to give you Ni, 3. Okay, and then PO4, there's 2 molecules. So PO4 in the bracket, and then you have 2. So this will be the formula for our nickel phosphate salt. So Ni3, PO4, 2, and don't forget about the phase solid. Example question 3. Given that the solubility product of magnesium carbonate MgCO3 and PbSO4, we have this value respectively, identify which ionic salt has a higher solubility and briefly explain it. So given the values over here, you can compare it this way. As we know that the higher value of Ksp, the more soluble is the ionic salt. So comparing between both value of Ksp, we can identify that the Ksp for magnesium carbonate is higher. So higher Ksp value means that magnesium carbonate is more soluble. Or vice versa, the lead sulfate has lower values of Ksp, which give you a less soluble ionic salt. So in your explanations, you can explain it this way. Higher value of Ksp, the more soluble is the ionic salt. And therefore, magnesium carbonate has a higher solubility as it has higher Ksp value. So now you have understand the term solubility, molar solubility, and solubility product, and how to write the Ksp expression. So the next thing is to solve a problems that involve solubility and solubility product. Alright, so since the Ksp or solubility product constant refer to the concentrations of this aqueous ion at equilibrium, then we need to use the ice table. So in problem solving of the questions, there is two scenario. So the first scenario, the question asks you to determine Ksp. So if the solubility of the ionic salt is given, you need to convert into molar solubility, or make sure the unit is mole per liter. Then you have to write the balance equation. After the balance equation, using an ice table, determine the concentrations of ion at equilibrium. That is to fill in your ice table first. Next, you need to write the Ksp expressions and calculate the values of Ksp. Another scenario is if the question asks to determine the solubility or molar solubility. So first of all, you need to have a balance equation. Then using the value of Ksp in the questions, construct your ice table, and from the Ksp expression, calculate the molar solubility S with a unit of mole per liter. If the questions request you to convert or write the solubility in unit gram per liter, then you have to do the conversions of unit. So let's just try the first example in the problem solving. So given in questions 1 here, we have the solubility of barium fluoride BaF2 in water equals to 0.628 gram per liter. Determine the solubility product of barium fluoride. And then the molar mass is already given in gram per mole. So first of all, identify this solubility has a unit gram per liter. Therefore, we need to convert into mole per liter. All right, and then after that, the questions, our target is to determine the solubility product. So I encourage you to write down the symbol first. So solubility product has a symbol Ksp. All right, so let's just convert the solubility into molar solubility, symbol S, and in this case 0.628 gram per liter. And to convert into mole per liter, we divide by the molar mass, so 175.3 gram per mole. So gram and gram cancel, it left with mole per liter. So in this case, we get the molar solubility equals to 3.58 times 10 to the power of -3 mole per liter. So the next thing we want to do is to write out the balance equation, which involves the solubility of barium fluoride. So barium fluoride, a solid ionic compound, when it dissociates in equilibrium, it will form Ba2 plus aqueous solution. And it will produce 2 F minus ion. So this is the balance equations for barium fluoride. All right, make sure that the equation is balanced. So fluorine, there is 2 on the left, and then you must make sure that there is 2 fluorine on the right as well. So after you have got this balance equation, the next thing is to create an ice table. Remember that for solubility product over here, we want to use concentration in your ice table. So initial concentration, change in concentration, and we have the concentration at equilibrium. So for solid barium fluoride, concentration is constant, so we just leave it blank or dash it. And the concentration initially for the ion will be 0. Why is it 0? Because you haven't dissolved the salt yet. So when the salt dissolves, then only we'll have the concentration. So in the second row over here, the change in concentration, we just plus x. So previously you do it plus x or minus x, but in chapter 7.3, we are using the molar solubility. So since the coefficient is 1, so you only plus 1s. So focus over here, we are using s instead of x. Okay, so similarly for fluoride ion, so since the coefficient is 2, therefore we will plus 2s. So the concentration at equilibrium, there's only 1s for barium ion, and there's 2s for fluoride ion. So this will be your ice table. So after you have completing your ice table, then come up with your KSP expressions. So KSP expressions equals to barium ion concentration and the fluoride ion concentration raised to power 2 as you have a coefficient 2. So it is very important that you will focus back on the balance equations over here. So power 2 come from the coefficients 2. And then we just substitute the S into each of your species over here. So barium have 1S only, whereas for your fluoride there is 2S. So 2S, make sure you put in bracket. Okay, make sure you put in bracket. The reason why is if you didn't put in bracket, 2S2 is 2S2. But when you put a bracket, then we will open up the brackets to give you 2 square into 4s squared. Okay, so it is very important for you to put in bracket. And then after that, we want to open up the bracket. So s times 4s squared to give you 4s cubed. Okay, so s multiplied with 4s squared to give you 4s cubed. Then we just substitute the value of molar solubility, the one that we have figured out just now. You have done conversion. Okay, so 3.58 times 10 to the power of negative 3 raised to power 3. And the final value of KSP equals to 1.835 times 10 to the power of negative 7. Bear in mind that KSP doesn't have any unit. So for question number 2, the solubility product KSP for magnesium phosphate, given you the formula Mg3PO42 is 1.4 times 10 to the power of negative 24. So calculate its molar solubility. So for this molar solubility, it has a symbol S and the solubility in gram per liter. So first of all, you need to come up with the balance equation. So we have the ionic salt Mg3PO42. So this is a solid ionic salt. When you dissociate in equilibriums, it gives you 3 ion 2 plus aqueous. And there is 2 molecules of the phosphate ion, PO43 minus. So this will be your balance equation. So creating your ice table, we have the initial concentration, change in concentration, and equilibrium concentration. So concentration here can also use the unit mole per liter. Alright, so the solid ionic salt constant concentration, so we dash it, and initial concentrations for Mg2 plus and phosphate ion is 0. The change in concentrations follow the stoichiometric coefficient. So for magnesium Mg2 plus, we plus 3s. So equilibrium concentrations, you have 3s. Whereas for your phosphate ion, the coefficient is 2, therefore we will plus 2s. So equilibrium concentrations equals to 2s. So once you have done and complete your ice table, then the next thing we want to do is the KSP expression. So KSP equals to concentrations of magnesium ion raised to power of 3. Coefficients equals to 3, so raised to power 3. And then the phosphate ion PO43 minus raised to power 2. And because it has a coefficients 2. And then you substitute the value of 3S into Mg2 plus 2S into phosphate ion. So it gives you 3S raised to the power of 3, 2S raised to the power of 2. And then open up your bracket, 3 cubed give you 27 S cubed. Multiply with 4S squared. So in this case, you will get a total S is equals to 108 S5. So when you multiply S cubed with S squared, it gives a total 3 plus 2, the power becomes 5. So in this case, KSP is given in the question. So 104 times 10 to the power of negative 24. Therefore, you need to figure out the value of your S. So the value of this molar solubility symbol S equals to 6.26 times 10 to the power of negative 6. And in this case, we have the unit, either it's molar or mole per liter. And then for part B, we want to convert the molar solubility into solubility in unit gram per liter. So using the values that we have found out earlier in part A. Alright, so the unit conversions, if we want to convert from mole per liter into gram per liter, we need to multiply with the molar mass. So in this case, the solubility equals to 6.26 times 10 to the power of negative 6 mole per liter times with the molar mass of magnesium phosphate, which give you the value molar mass 262.9 gram per mole. So in this case, mole and mole cancel, which leave the units gram per liter. So the final value for the solubility equals to 1.65 times 10 to the power of negative 3 gram per liter. Alright, so please have a try on your exercise 1, question number 1 ABC, question number 4, question number 5 A and B. This question will be discussed in the hybrid lesson in your next lesson. So that's all for the video over here. Thank you.